Finishing up chapter 4. Here we are in chapter 4 and we're ready to roll. Just a few more things to wrap up and you'll be ready to take your test after some practice. Exponential growth and decay. Interesting stuff. Growth and decay. Very similar. All they're different in is just one simple constant. Positive means growth, negative means decay. That makes logical sense, doesn't it? So we'll look at population, we'll look at radiation decay, and if we're Marie Curie, we should have stayed away from the radium. Okay, this is what it sort of looks like for us. There's the derivative, there's our constant, and there's a variable. And I'm going to set up the pen so I can make some notes. One thing we might want to notice because of the last section, remember in the last section, 3.8, we talk about differential equations. This is similar to a differential equation if we multiply both sides by dt. dy equals k times y times dt. dt is one constant, or one variable, and that's our differential one. And in some instances, like physics and so on, you might see something like this. Here's our exponential growth and decay, both of them all in one. Right over here is sort of our master model. This represents what is changing. This is some constant depending on our particular application. And this represents that constant I mentioned earlier. If it's positive, we're talking about an exponential growth. If it's negative, it's talking about an exponential decay, like radioactivity, for example. T represents the time, and that might be in seconds, minutes, hours, days, almost centuries, really, depending on what the situation is, what the application is. Radioactive decay is measured in half-life. Now, what does that mean if you haven't run into it or haven't run into it for a while? Let's suppose we've got an element here, and we're going to call this element, let's see, we'll just use a W. I know W actually represents an element. We're just going to pick something. So let's suppose we've got about 10 grams of this element, and then we wait a period of time. That period of time is called half-life. Better written like that, of course. After waiting that particular period of time, we go over here and we don't have as much left. In fact, it's called a half-life because after that particular period of time, only half of that material is left. If we wait that same amount of time, so if this is 17 years, that's 17 years. What do we have left? Half of what we had back here. So it'll be 2.5 grams of that element. That's how a half-life works. Here's examples of some common radioactive isotopes. Hopefully they're not common to where you live. Uranium-238, you might use that to make a bomb. Plutonium, carbon. Carbon-14 is used for dating. Typically, carbon has an isotope of 12. That's the common one. The radioactive one is carbon-14. And there's radium, einsteinium, my favorite because I like Einstein, and nobelium. Notice the half-lives. Up here, a long number of years. You're not going to wait until uranium-238 disappears, or half of it disappears. Or plutonium for that matter. That's a long time. Or that. Now einsteinium is a different story. You could actually watch that decay 276 days later after you'd gotten that lump of einsteinium, only half of it would be left. Wait another 276 days, only 1/4 of it is left. Nobelium, you better not blink your eyes because that thing's going fast. So here's how we model the exponential growth and decay. First of all, we have to have two sets of conditions. For example, our conditions might be, where am I here? There we go. Number of grams of whatever we've got, and how much time has elapsed. When you start this experiment, if you want to call it that, your time elapsed would be a 0. And this would be your initial amount. Start with a certain amount. After a half-life in some situations, that time elapsed is what T represents. The K is going to tell you whether it's growth or whether it's decay. If it's positive, you have growth. If it's negative, you've got decay. If you get T equals 0, that means you're at the very beginning of your, quote, experiment, unquote. Using those conditions, you're going to have two sets of conditions, two amounts with their related times elapsed. Using that, you can create a model. Your model will look like this, but some of the numbers will be filled in. The C will be filled in, and the K will be filled in. And you'll be able to use that for situations where something is changing exponentially, and you know the time, you know the constant. If you know everything over here, you can find out how much of something there is, or whatever you're talking about. We need some examples, right? There's a substitution. Use the model. So here's how it works. First of all, the two conditions. Sneak back here. Number one, you need two sets of conditions. What have you got? Well, you've got, first of all, here are your conditions. Number one, 2 days. After 2 days, you had 100 flies. Condition number 2, after 4 days, what do you have? You have 300 flies. I hope you're not eating while you're watching this. And then you're going to use that to create a model. And your model will allow you, once it's complete, to take a an elapsed time and estimate how many, in this case, how many flies there are after that period of time. So we'll get a model, and what we want to know, we want to find the number of flies at 5 days. Okay, first of all, we've got two sets of conditions. We've got, in fact, we're going to switch those around because the days determines how many flies there are. So what we're going to do is we're going to put flies first, number of flies, and time second. So we've got 100 flies after 2 days, and we've got 300 flies after 4 days. So how do we use that? Well, let's go back here a second. Here's the model that we're trying to get. What do we have? So our model is going to start looking like this. This is the model with nothing filled in yet. So what does this first one mean? Well, this is the number of flies. That's going to be the y. So for the first condition, we've got 100 equals. We still don't know what C is. Doggone. E. We don't know what K is. That's the other thing we need to find. And for this condition, we've gone 2 days. 2 days have elapsed. So how do we do that? We've got 100 equals. I'm just going to clean up here a little bit. E to the 2k. What I'm going to do next is I'm going to solve it for C. I can solve it for C by dividing by this e to the 2k. So C equals 100 over e to the 2k. That's using condition number 1. Condition number 2, what do we have? Condition number 2 says C equals y equals C E K T. Now from the other one, we have an expression for C. So what we're going to do in the second one is we're going to put in what we can. For the second condition, we've got 300 flies, so 300 is the y value. We'll get C from the other one. C from the other one is 100 over e to the 2k. That's C, and we've got e to the k. Now this is the second condition here, and we had 4 days gone by. So that's the second condition, but instead of putting the C, we got the C that we solved for from the other one. So what does that give us? Okay, let's clean this up a little bit so we can work with it a little bit easier. We've got 100 over e to the 2k, and we've got e to the 4k here. Well, notice that we can divide both sides by 100. That'll give us 3 equals, and then we've got e to the 4k, e to the 2k, we're dividing, so we'll subtract the exponents, and we'll end up with 1 e to the 2k. How do we solve that one? We've already talked about things similar to that. This k that we'd like is in the exponent. We can't work with that directly, but what we can do is convert this to a logarithmic one. The inverse of e to a power is the natural log. So we'll take the natural logarithm of the left side and the natural logarithm of the right side, 2k. Now that natural logarithm and the e to the power are inverse operations. So what we end up with is the natural logarithm of 3 equals, and these two cancel each other out, so to speak. And over here we've got 2k. Divide by 2, and we have a way of writing, writing k. That's our k. And notice 2 is a constant. Natural logarithm of 3 is also a constant. So we can use our calculator and we can write down what that is. I don't have it right in front of me, and I'm not going to grab the calculator. We'll see in a moment. So we've got k. So what is c? We need the c also to have our model. Well, right up here, when we were working with our first condition, we said c equals 100 over e to the 2k. Hey, we just found out what k is exactly. All I need to do is put that into this formula, and I can get what c is. So, that's what we did. We took the two conditions and put those together. Took the first equation and solved it for c up here at the top. We took that c and we put it in this equation, which made it look like that. Divide both sides by 100, and it looks like that. And then take the natural logarithm of both sides, divide by 2, and there's our k. In particular, it's 0.5493. I didn't have it memorized. That's why I didn't write the whole thing down, but I did remember the 0.5. So we've got k, just put it into that equation we had earlier, and we can find that c is about 33. So the exponential growth model, putting c in and putting k in, here is our model. So we needed the model because we wanted to find out how many flies at 5 days. We've got our model. All we have to do is put the 5 in where the t is. Put the 5 in there, a little bit of calculator work. Hopefully you're not going to try to do this by hand. And you've got about 504 flies after 5 days. And we've got the answer complete. We've got our model, and we've got the answer to the question we were trying to get to. If your model, the model you're working on, doesn't come from something that has a base of e, you can make this adjustment and you can still make a model. Notice, and this is a good thing for you to check on, is e to the natural logarithm of a, it's actually a. Which gives us just what we have. So if you have a model that has something other than e as the exponent, you could work it like this and then come back and put the A in. But E is much more often used, and it's much more convenient to work with because natural logarithm is so great, and e to the power is so great to work with. Another example we've got. So it says 4 months after discontinuing advertising, sales have dropped from 100,000 to 80,000. And we know for some reason that it's an exponential pattern of decline. What will be the sales after 4 months? So what we're looking for oops, sorry about that. Scratch that one out. That's our goal. We need conditions. Now if you read this carefully, it says sales have dropped from 100,000 to 80,000. If you read this carefully, then at time equals 0, you had sales of 100,000 MP3 players. Where is it? 4 months, which means T equals 4 months. Your sales are down to 80,000 MP3 players. Those are your conditions. In order, first and second. So, and don't forget, before we go on, notice that the 100,000, where am I here? The 100,000 MP3 players are at the very beginning. The 80,000 is after 4 months. Now it says 4 months after discontinuing, it's dropped. Use an exponential pattern. What are the sales after another 4 months? So what we're interested in is what is it at 8, because it's at 4 more months. This is what we're actually looking for. So this is what our model is going to look like, because we believe it's an exponential growth. So we'll take the initial information, we'll put that in there. 100,000 is how many MP3 players are sold. C we don't know yet. E is E. And K we don't have. But K is 0 up here. Actually is the K that we'd like to have times 0, because that's the initial condition, which means time equals 0, which makes things very nice. So if you solve that, this, almost anything to the 0 power is 1, so that's C equals 1,000. We've got one of our important parts to the model. C equals 1,000. So right now our model looks like this. 100,000 e to the k t. If we got k, we'd have our model. And then we could solve our problem. So there's our model without the k, or with the k, but unknown. Put the second set of conditions in. Remember, we sold 80,000 MP3 players after 4 months. Solve that as an exponential equation. You've got a base of e, good news. Take the natural logarithm of both sides. And we've got the natural logarithm of 0.8 equals 4k. We'll be dividing both sides by 4. Before we do, just one simple note here. We're taking the natural logarithm of something, this 0.8 is less than 1. Of course, it has to be positive, because to take the natural logarithm of a number, it has to be a positive number. But the thing to take note of is because this is less than 1, e to the 0, remember, is 1. If we get 0.8, then we have to have a smaller exponent, which means be a negative exponent. So when we get this, throw it into your calculator for a second. Hit pause, put that in your calculator. See, this is a negative one because remember, logarithms are exponents. This is the exponent that e needs to give you 0.8. Moving along. So we multiply both sides by 1/4, or divide by 4, and there's our k. Hit the calculator, and there's our k. Negative 0.0558. So the model you have the c, you have the k, you've got your model. Now what did we need? We needed to know how many MP3 players we could sell after 4 more months. We sold 100,000 at the beginning, which means time equals 0. We sold 80,000 at 4 months, and we want to know what it is 4 months after that, or at 8 months. So we'll put the 8 in for t, and get our answer. After 4 more months, we'll be selling 64,000 MP3 players. That sounds pretty good, but not very good compared to the 100,000 that we were selling with advertising. Excuse me. And that's the end of our story for Chapter 4. If you need some help working some of those problems, stop by the office. If it's Monday, Wednesday, or Friday, I'm there between 9:30 and 11:30, and then after 12:30. Or if that doesn't work with your schedule immediately, just let me know, and I'll stay at a different time, or come in on Tuesday and Thursday. Sometimes I do anyway. There's no imposition at all. Or if you're in quarantine, for example, or if you just don't feel like driving in from wherever you live, you can do a Zoom session. So don't forget. Okay? Well, keep smiling, and I'll see you next time. Bye-bye.